In this section on linear transformations, we saw some examples of transformations of the plane, such as reflections and rotations. For example, the transformation that reflects about the y-axis was given by this matrix. There is a transformation that expands each vector vertically. So let's say you had a vector here. What it does is it expands it vertically. And let's say V was down here. Then it expands it vertically away from the x-axis. Like that. Okay, every vector gets pulled away from the x-axis. The matrix for this transformation is given by this. Where k is bigger than 1. Let's look at the case where k equals to 2. So a is equal to this. Applying a to the point 1, 1 gives you this. Okay, so here's 1, 1. And here's 1, 2. Okay, so it stretches it here vertically. If we apply a to 1 minus 1, we get this. So the vector 1 minus 1 gets sent here to 1 minus 2. Note that each vector on the y-axis is scaled by a factor of 2. For example, if we apply a to 0, 3, we get 0, 6. So here's 0, 3. And it gets sent to 0, 6. Okay, notice that 0, 6 is 2 times 0, 3. So the matrix A scales this vector by a factor of 2. Okay, symbolically this is written like this. A times V equals lambda times V, where lambda is the scale factor and V is our vector 0, 3. Now, if this equation is true for some non-zero vector V, and lambda some scalar, then lambda is called an eigenvalue of A. And V, the vector V, is called an eigenvector of A. And it's an eigenvector of A corresponding to lambda. In our example, 0, 3 is an eigenvector of A corresponding to the eigenvalue lambda equals 2. Of course, 0, 3 isn't the only eigenvector corresponding to the eigenvalue lambda equals to 2. Every vector on the y-axis gets scaled by a factor of 2. So any vector of the form 0t, where t is not 0, is an eigenvector of A corresponding to lambda equals to 2. Notice that vectors on the x-axis are not affected by the vertical expansion. So if I apply the matrix A to some arbitrary vector on the x-axis, then I get the same vector, which is 1 times the vector. So if I graph this, here's some vector x0 on the x-axis. If I apply A to it, I just get back the same vector, 1 times that vector. So applying A to this vector simply scales it by 1. Any vector of the form x0, where x is not 0, is an eigenvector of A corresponding to the eigenvalue lambda equals to 1. Note that not all vectors in the plane are scaled by some scalar lambda. In our example, only vectors lying in the x-axis or y-axis are scaled by some scalar k. These vectors are special and are the eigenvectors of A. For a fixed eigenvalue lambda, the set of all vectors v that satisfy this, the set of all vectors v that satisfy this forms a subspace and is called the eigenspace of lambda. Okay, this set consists of all eigenvectors corresponding to lambda and also the 0 vector. Okay. In our example, the eigenvectors corresponding to lambda equals to 2 are all the non-zero vectors on the y-axis. If we include the 0 vector, the set of all vectors on the y-axis is the eigenspace of lambda equals to 2. Okay, so the eigenspace of lambda equals to 2 is the y-axis itself. It's all those vectors along the y-axis. Note that this eigenspace is a one-dimensional subspace of R2. So this is the y-axis, and it's a line and so it's a one-dimensional subspace of R2. R2 is the whole plane. The set of all vectors on the x-axis is the eigenspace of lambda equals to 1. Okay. So that's this, the x-axis. Okay. This eigenspace is also a one-dimensional subspace of R2.